Hello and welcome to MicroLive. This week, in the second part of our look at word processing, what's on the market for the business user and how do you choose the right package?
Has the silicon chip had its day? We look at research which may lead to the optical computer.
And we go to Scotland to see a system for the fire brigade that has to work every time, no matter what the emergency.
Well, I don't suppose you'd fancy putting your home micro into here and sending it off at 240 miles an hour. But inside this dragster, there, if I can get at it, there is a computer. There it is, and it's used for monitoring the machine's performance, the fuel flow and the wheel and clutch slip. Now, this kind of control application is way beyond the scope of the home micro. For one thing, it's a hostile environment. But more to the point, a lot of the micro would be wasted. You don't need a monitor, of course, and you don't need the disk drive. You don't even need the keyboard. And many of the functions of the main circuit board become redundant too, the sound and the video chips, for example. But add some smart new chips and a lot of interfacing, and you end up with something like this. This board is the brains behind the car's brawn. It's being developed to control various functions on the car, and eventually it's planned to use one in a vehicle like this. It'll be used in an attempt on the world's wheel-driven land speed record, which currently stands at 409 miles an hour. The board is called Scorpion, and it was designed by Peter Miller. Peter, welcome. What can it do?
Well, it's a general-purpose control computer. It has a microprocessor. It has 24K of RAM in those chips, with battery backup, which also keeps the clock and calendar running. There's a 32K language in there, and numerous interface ports.
By interfaces, those are what you call inputs and outputs.
That's right. Yes.
Now, inputs, in plain terms, are sensors, are they? Ways in which the board can learn about the outside
That's
world.
Right.
What sort of things?
Well, we've got digital sensors like the switch. There are analog sensors like this temperature probe. And this device can measure the speed of rotation of a shaft, the direction of rotation, and also the absolute position of the shaft.
Presumably there's something very much like that on the car.
Yes, so there are a number of those, monitoring different functions. And also, one can drive this small camera. It's a solid-state camera, 256 1:8 resolution, and it plugs straight into the control card.
That is an input?
That's right. Yeah.
That's quite sophisticated for a small board.
It's not what you expect on a card of this size.
Those then are the inputs. What about outputs? What can it drive?
Well, again, you've got a variety of devices. There are various motors, DC motor, stepper motor, servo motor, even a Lego motor, and valves, relays.
Or if you really want to get complicated, we've even got a robot arm.
Well, this is a robot construction system. It's used in schools, and you can build it up in many different ways.
So we've got, what, 1, 2, 3, 4, 5 different motors there.
That's right.
Right, so those are inputs and outputs. We've got a very simple demonstration over here which uses much simpler inputs and outputs. This one is the input. It's a pressure pad, the sort of thing that you might get on a burglar alarm. And the output itself is just that light bulb there. But of course, between the input and the output comes the decision-making, the program. What kind of language have you used?
Well, a lot of control languages use the fourth approach, and I gather last week that was described as a write-only language.
A write-only language, yes.
Well, ours is definitely read-write, and it's based on more on Logo Pascal approach.
Can we see some code?
Got a routine called light, which is defined like this. It's a routine called light. It forever goes round this loop, which checks input 6.
That's the mat.
That's
yes.
right, for a condition, and turns the light on or turns the light off, depending on the result.
So the 4 is output channel 4,
That's right.
The light itself. I see. Well, that looks very easy to understand, and let's test it out. Sure enough, if I push on here, does it work? It does. It truly does. But that's a fairly trivial kind of application, isn't it? You don't even need a micro for that. Have you got anything a bit more realistic?
Yes, I mean, a program we've made up of many routines like this. We've got a slightly more complicated routine in this one, called door. The routine door goes round the loop forever. Repeating 4 times, it gets a key from the keypad, and it checks each one for being in the sequence 1, 4, 16, 13.
So this is a password, a code?
That's right, that's a password to get in. If at any stage you get it wrong, it throws wrong, which takes you back to the beginning. Otherwise, it gets to the stage of opening 7, waiting for a second, and then closing 7.
Well, at vast expense, we've provided you with a door. Perhaps you could pull that across and show us how it
well,
works.
this door is connected to port 7, and if I don't know the password, I can type away and nothing happens. But if I go around the keys in the correct order, hey presto.
Magic. And of course, at the same time, the light is still working. So this is a true multitasking language.
Yes, it's a multitasking language. You can run virtually any number of tasks. You can hundreds of tasks, although the processor time will be shared between them, so that it will go quite slowly if you did have that many tasks running.
But why are we using a BBC Micro here? I thought this was a self-contained unit.
Well, the BBC Micro is a convenient keyboard and screen. It connects to the controller over a serial interface. You can use any computer in place of the BBC, and now we've programmed it, we can actually turn the BBC computer off. And things still continue to run.
Yes. Yes, and the light still works. So who's using these?
Well, it's used in schools, colleges, laboratories, industry, all over the place. And it's also finding its way into specialist applications, specialist products. We've got one behind us, actually. If you were wanting to do an audiovisual presentation, you might have something like this. You'd have some slide projectors, you'd have a sound, you'd have the lighting to control, possibly a screen to bring down.
That's a great deal to look after if you're also reading a script, if you're also looking at your notes.
That's right. So this unit here tries to simplify it.
So if I just press the start, it will all happen, I take it automatically?
That's right.
See, the lights should
lights
go
come down.
Yes, they do.
The
Sound starts up. And the slide start. Now, those are, of course, outputs. What about inputs? Are there any in this application?
Well, there's a certain amount of feedback provided. There'll be feedback with an electric screen about whether the screen's down or up, whether various devices are connected or not. And also, of course, there's the input from your pressing the keys on the keyboard.
Right. Thank you, Peter. Thank you. A very versatile unit. Many thanks.
Thank you very much.
Well, if you'd like to find out more about Scorpion, the details are in our notes. The Strathclyde region covers 5,500 square miles of wood, field and isolated islands. It's a fire brigade's nightmare.
Fire Brigade. There's a fire at Hartfield.
The control room of the Strathclyde Fire Brigade houses the most advanced computer call-out system in Britain. It handles all fire calls immediately, working out how to get the right equipment to the right location without error.
There's a fire at Hartfield.
Yes, what's the address?
Hartfield.
Hartfield. H-U-R-T.
Yes, hurry up.
In the heat of the moment, place names are easily misunderstood and slightly misspelt. But if the computer cannot match the name, it's programmed to find all the nearest alternatives.
What town is that in?
Eldersley.
The operator can then work out which is the correct name by its location.
Could this be Hartfield Farm? H-A-R-T. Hartfield Farm, Eldersley.
Yes, that's right.
It is. The Fire Brigade will attend. Thank you.
When the operator is satisfied that the name is correct, the computer is asked to select the nearest fire engines available. If the operator then accepts this advice, the system is told to go ahead. Details of the fire are transmitted down a line to the selected fire station.
The crew at the fire station now obtains a printed message giving them the details of the incident that they have to attend to. That has advantages in that previously a person would be involved receiving that information over a telephone and would perhaps be the only person at that moment in time with knowledge of the nature of the call-out.
Freezing fire, lads. Quick mobile to incident.
The computer is told that the engine's on its way by this button box, operated by the crew from the cab. Each key press sends a coded radio signal back to base. The firemen do this every time they move between zones on the fire station's map. This end of the system relies on one of the older microprocessors still in production, the Z80. Not exactly state-of-the-art, but the important thing is to use proven technology where lives may be at stake.
due course, one can envisage many fire brigades having printers in their appliances, and this would enable the control operator to send ongoing and updating information during an incident, and again the fireground crews would have more pertinent, legible information, are less concerned about garbled or clash speech on an open channel radio.
Even though the system is still rudimentary, it gives clearly understood information, and the brigade say it's already cut the time it takes to alert a station in half.
Amazingly, if you report a fire in London, there is still no computer ready to work out which fire engine to send. As in London, they have to use operators leafing through a card index of available fire equipment. This is because, although the London Fire Brigade commissioned a computer call-out system from computer manufacturers Marconi 3 years ago, Marconi still cannot get their system to work. Last week, in secret factory tests, Marconi found that their system took all of 10 seconds every time it updated a new screen of information. On the Strathclyde system, this vital updating is immediate. The London Fire Brigade already has a brand new control room in place, but unfortunately no reliable system to plug it into.